Hello everyone, welcome to my YouTube channel. I hope you all are fine by grace of Almighty. Today I am here with a video on enzyme-linked immunosorbent assay, ELISA. So, let's start. What is ELISA? Enzyme-linked immunosorbent assay, ELISA, also known as an enzyme immunoassay, EIA, is a biochemical technique used mainly in immunology to detect the presence of an antibody or an antigen in a sample. The ELISA has been used as a diagnostic tool in medicine and plant pathology, as well as a quality control check in various industries. What is ELISA mechanism? Performing an ELISA involves at least one antibody with specificity for a particular antigen. The sample with an unknown amount of antigen is immobilized on a solid support, usually a polystyrene microtiter plate, seen detailed in a section of ELISA device, either non-specifically, via adsorption to the surface, or specifically via capture by another antibody specific to the same antigen, in a sandwich ELISA. After the antigen is immobilized, the detection antibody is added, forming a complex with the antigen. The detection antibody can be covalently linked to an enzyme, or can itself be detected by a secondary antibody that is linked to an enzyme through bioconjugation. The part of antibody incubation of ELISA is similar with that of Western blot. Between each step, the plate is typically washed with a mild detergent solution to remove any proteins or antibodies that are not specifically bound. After the final wash step, the plate is developed by adding an enzymatic substrate to produce a visible signal, which indicates the quantity of antigen in the sample. ELISA protocols. There are 5 types of ELISA, thus, about ELISA protocol, a few differences exist amid indirect ELISA protocol, direct ELISA protocol, sandwich ELISA protocol, competitive ELISA protocol and ELISpot protocol. However, the main ELISA principle and lots of procedures are the same. General ELISA protocol includes plate preparation, assay procedure and calculation of results. Plate preparation. 1. Dilute the capture antibody to the working concentration in CBS. Immediately coat a 96 well microplate with 100 microliters per well of the diluted capture antibody. Seal the plate and incubate overnight at 4°C. 2. Aspirate each well and wash with at least 300 microliters wash buffer, repeating the process 2 times for a total of 3 washes. Complete removal of liquid at each step is essential for good performance. After the last wash, remove any remaining wash buffer by inverting the plate and blotting it against clean paper towels. 3. Block plates by adding 300 ml of blocking buffer to each well. Incubate at room temperature for a minimum of 1 hour. 4. Repeat the aspiration/wash as in step 2. The plates are now ready for sample addition. Assay procedure. 1. Add 100 ml of sample or standards in sample dilution buffer per well. Seal the plate and incubate 2 hours at room temperature. 2. Repeat the aspiration/wash as in step 2 of plate preparation. 3. Add 100 ml of the detection antibody, diluted in antibody dilution buffer, to each well. Seal the plate and incubate 1 hour at room temperature. 4. Repeat the aspiration/wash as in step 2 of plate preparation. 5. Add 200 ml of substrate solution to each well. Incubate for 20 minutes at room temperature. If substrate solution is not as requested, the incubation time should be optimized. Avoid placing the plate in direct light. 6. Add 50 ml of stop solution to each well. Gently tap the plate to ensure thorough mixing. 7. Determine the optical density of each well immediately, using a microplate reader set to 450 nanometers. Calculation of results. 1. Calculate the mean absorbance for each set of duplicate standards, controls and samples. Subtract the mean 0 standard absorbance from each. 2. Construct a standard curve by plotting the mean absorbance for each standard on the y-axis against the concentration on the x-axis and draw a best fit curve through the points on the graph. 3. To determine the concentration of the unknowns, find the unknown's mean absorbance value on the y-axis and draw a horizontal line to the standard curve. At the point of intersection, draw a vertical line to the x-axis and read the concentration. If samples have been diluted, the concentration read from the standard curve must be multiplied by the dilution factor. 4. Alternatively, computer-based curve-fitting statistical software may also be employed to calculate the concentration of the sample. ELISA application in food industry. ELISA is popularly used in the food industry to detect the presence of allergens for legally required ingredient labeling. This application benefits greatly from the sensitivity of ELISA and can detect levels of potential food allergen contaminants at concentrations on the low parts per million (ppm) scale. Since 2005, the FDA has required manufacturers to label their products with regards to 8 specific allergens: milk, eggs, fish, shellfish, peanuts, wheat, soybeans, and tree nuts. These allergens are responsible for over 90% of the documented food allergen-related cases. In food industry, the 2 most common and preferred methods for the detection of allergens are ELISA and PCR. ELISA methods detect the actual allergen protein molecule by binding antibodies to the allergen and then using an enzyme-linked conjugate to create a colorimetric change that can be measured. There are certain instances, though, that ELISA methods should not be used. Some matrices can interfere with the ELISA method, such as chocolate, or can cause cross-reactivity as seen between different types of nuts. This method is also not the most suitable for cooked or heated products because the protein molecules are denatured or broken down and the allergen is no longer detectable, but may still cause problems to sensitive individuals. PCR methods, which are more sensitive and detect the DNA molecules of these allergens, can be used in raw uncooked products and are not affected by the heating process because DNA typically remains intact after being exposed to the cooking temperatures of most foods. PCR methods are also not subject to the typical interferences that inhibit ELISA-based methods because the DNA is purified away from these inhibitors before analysis begins. PCR, however, cannot be used on all products. Oils and other products, such as milk or egg whites, cannot be tested by PCR because they do not contain DNA. These products must instead be tested using ELISA-based methods for detection. Product testing in the food industry has historically centered on detecting contaminants that could cause outbreaks or illness. Various bacterial and fungal pathogens were the primary agents of concern, followed by chemical contaminants. With today's high throughput and automated processing, additional contaminants such as food allergens are becoming an increasingly important issue in food safety. That's it from today's video. Thank you for watching. Take care of yourself and family. Do subscribe my channel and share it in your circle. Take care. Goodbye.